So the next violation is correlated observations. Correlated observation refers to the situation in which the residual terms are correlated with one another. Assumption 3 says that observations are uncorrelated. This correlated observation or this assumption breaks down in studies with time series data. Variables such as sales, employment, and asset returns exhibit business cycles. As a consequence, successive observations are likely to be correlated. In this section, we have a model in which y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus epsilon, where y represents sales in $1,000 at a sushi restaurant, x1 and x2 represent advertising costs in dollars and the unemployment rate in percentages respectively. To detect correlated observations, we plot the residuals sequentially over time. So again, we use data analysis and regression, and then we select input y range. In this case, it's sales, and x range or the predictor variables are advertisement costs and unemployment. Labels are included, and let's say our output range is in G. We don't want residual plots, we just want the residuals this time. And you can see the residuals here. So to detect, we need to plot residuals sequentially. So insert scatter plot. This creates a placeholder for scatter plot. Right-click, select, add, and our x values is time or date, and y values are the residuals. And then click OK. One more time, OK. So here, residuals shows a wave-like movement. It's going up and then down and up again. So they first cluster here below 0 and then cluster above the horizontal axis and so on. Given this pattern around the horizontal axis, we conclude that observations are correlated. So you can see a pattern of residuals here. Therefore, assumption 3 is violated. The next topic I'm going to talk about is multicollinearity. Multicollinearity exists when two or more predictor variables have an exact linear relationship. Consider a model like y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. And let's assume that this y is the bonus of a car salesman, and x1 is the number of cars sold. And here x2 is the number of remaining cars. And if all car salesmen started with the same inventory, we have a case of perfect multicollinearity. That means x2 remaining cars is equal to 1 minus x1, which is number of cars sold. Perfect multicollinearity is easy to detect because the model cannot be estimated. However, if x2 represents the proportion of positive reviews from customers, we have some multicollinearity because the number of cars sold and the proportion of positive reviews are likely to be correlated. In most applications, some degree of correlation exists between the predictor variables. How do we detect multicollinearity? We check the regression results, and if you see that you have a high R-square and significant F statistics coupled with individually insignificant predictor variables, then you may be suspicious about multicollinearity. Or you may have high correlations between the predictor variables, or you may have wrong signs of estimated coefficients. You might have insignificant important predictor variables, or if you are using a software package, most of the software packages report variance inflation factor, VIF, exceeds 5 or 10, indicates a multicollinearity problem. Here we have median home value data in dollars. And this is our response variable, and median household income in dollars, per capita incomes in dollars, and the percentage of owner-occupied homes as the predictor variables. So I estimate the model using with all predictor variables. Surprisingly, when you look at here, per capita income variable has a negative estimated coefficient with a p-value of 0.309, is not even statistically significant at the 5% level. Multicollinearity might be the reason for this surprising result because household income here and per capita income might be correlated. So I computed the correlation between these two variables and find out that it's 0.858159, which suggests that multicollinearity is rare because these two variables are highly correlated. Then I estimate the model by dropping per capita income, and then I estimate the model by dropping household income. Between this model 2 and model 3, model 2 is preferred to model 3 because of high adjusted R-squared compared to model 3. But choosing between model 1 and model 2 is not clear. In general, model 1 with the highest adjusted R-squared value, which is 0.8071, is preferred if the sole purpose of the analysis is to make a predictions. However, if the coefficient estimates need to be evaluated, the model 2 may be the preferred choice. So if you have a multicollinearity issue, to remedy the problem, you can drop one of the collinear variables, or you can obtain more data because once you have more data, the correlation between the variables gets weaker, or you can express variables differently, or you can choose to do nothing. And the final violation that I'm going to talk in this video is excluded variables. So if you remember, assumption 5 says that the error terms is not correlated with the predictor variables. In general, this assumption breaks down when important predictor variables are excluded. If one or more of the relevant predictor variables are excluded, then the resulting regression coefficients are not correct. Suppose, let's say we want to estimate y is equal to beta 0 plus beta 1 x plus epsilon, and y is the salary, and x is years of education, number of years of education. Note that the omitted innate ability, so there should be another variable, let's say this is x1 and x2, which is your ability, is correlated with the years of education. Now consider someone who is highly educated and also earns a high salary. The model will associate a high salary with education. So if you find that high salary, you have a high salary with higher years of education, then you conclude that, okay, years of education increases your salary. But in fact, it may be the person's unobserved high level of innate ability that has raised both education and the salary. In sum, this violation leads to unreliable coefficient estimates. Even some estimates may have the wrong signs. So what is the remedy here? It's important to include all the predictor variables. An important first step before running a regression model is to compile a comprehensive list of potential predictor variables. We can then build down perhaps a smaller list of predictor variables using the adjusted R-square. So let's say you find out 5 predictor variables and you compare the adjusted R-square of model 1 is with 4 predictor variables and model 2 is with 5 predictor variables, and choose the one with higher adjusted R-square. A quick summary. It takes a practice to become an effective user of regression methodology. We should think of regression modeling as an iterative process. So before you start estimating your model, make sure that you check the residuals and plot the residuals and see if there are violations of any assumptions.